Okay, in this video we're going to go over some examples of an OCR topic, which is about finding the CDFs and PDFs of a related random variable to a given random variable. The one overriding thing we'll see is it's the CDF we have to work with and manipulate, regardless of whether it's the PDF that we've been asked for or the PDF that we've been given. The first example is about the original distribution is a uniform distribution, including the equally likely bit between 1 and 3. The way we write that is uniform between 1 and 3. I'm not going to go into detail as how to find the PDF of that, the CDF of that. We don't, for the sake of this question, we don't need to write it out in full like this. I'm just putting it here to remind you that that's what the CDF of this particular continuous uniform distribution will look like. It's got to be linear, going between 0 and 1. So, and if you look at it, it's linear between 0 and 1, between the values of x of 1 and 3, that has to be the function. And have a look back at your work on that if that's a little bit rusty. But yeah, it's got to go like that. For x values between 1 and 3, it's got to go between y values between 0 and 1. So we can easily work out that function for it. I'd say it doesn't need to be written out in that kind of fully like that for the sake of this question. I'm just doing it like that just to remind you of what it should look like. Okay, so I might actually get rid of it now just for the sake of what we need. That's all we need really for this part of the question. Okay, right, so then what we need to do is relate our new random variable for y to it. Now, because it talks about the area of the square, well, we know what the area of a square looks like. So y equals x squared. Right, and we want to find out the CDF for this in order to, I know it asks for the PDF, but as I say, regardless, we need to find the CDF first. So let's call it capital G to avoid, because it's not going to be the same function as the f, is it? So I'm going to call it capital G of little y, which will refer to the probability of y being less than or equal to y. Remember, that's what a CDF does. It gives you the probability of a particular observation of that random variable being less than a particular number. That's what the CDF gives us. So we want the one for capital Y and little y here. Now this is where we get to relate it. So we have probability that y is less than or equal to y. So that's x squared, because we know that y equals x squared is less than or equal to y, which gives us the probability. Now we can take square roots on both sides. Okay, and lo and behold, we're kind of close to where we can basically replace, we're now close to our original CDF of interest, but now except we've now got capital, the square root of little y in the function. So that's going to be equal to f of the square root of y. Okay, so we can therefore say that gy is equal to f of little square root of y, which is equal to square root of y put into here. Now, if it were only the CDF that I needed, I would actually now perhaps write that out fully. Let's just actually take this down a bit. So I've got the thing I want. So if I wanted it fully now, I'd go 0, 0, 1, and then I would actually work with the inequalities. Square root of y has got to be less than or equal to 1 and 3, and so on. But I'm actually wanting the PDF. The question actually asks for the PDF. Yeah. So we want the PDF of y. And in order to get the PDF of y, let's call it little g of y, we need to differentiate the CDF. And differentiating the CDF, differentiating that, I won't make a song and dance about that. That's basically y to the half over 2 minus a half. So differentiating that, I'm going to get a quarter y to the minus a half. But we want to fully define it, so let's do it with the kind of correct, fully specifying it with the 0 over y's bit. Quarter y to the minus half. And remember, the actual variable that we've got now is y, but the original one in our function was x. So we need the square root of y to be less than or equal to 1 and less than or equal to 3 and 0 otherwise, but we can't leave it like that. So so now I need to finally to get it back in, fully specified and properly, any kind of silly little things like square root of y's in there. So that's y is greater than or equal to 1 and less than or equal to 9 and 0 otherwise. Okay, so that's it for question 1. So we had to, in this case, we had to kind of find out what the CDF was, then find the CDF of the related function here, and then differentiate to work out the PDF. The other thing to watch out for is we have to obviously change the actual inequalities because the variable has changed. The original function for f was related to x, so we need to change it so it's related to y. So we have to change that as well. So wherever you see x, you replace with the square root of y in this particular case. Let's do another example. Okay, so this is in some ways more complicated, but in some ways simpler because we've already got the CDF and it only wants the CDF. The question, strangely, I prefer not to call it capital F-Y there because it's going to be different to our original function. So I'll call it capital GY. So we want to find the CDF where the thing is related by this function here. So again, we want the CDF, which is GY, which basically refers to a particular observation of this being less than a particular value y. Now that's equal to, capital Y is equal to 4x squared, less than or equal to y. And now we need to refer it back to x, so that's x less than or equal to the square root of y over 2, which is precisely because this thing here gives us the probability that capital X is less than or equal to x. So that is going to be f of square root of y over 2. So I'm going to replace the square root of y over 2 in everything here, including the inequality. So I have g of y, which is the same as f of the square root of y over 2, basically. So replacing the square root of y over 2 in there, I get 0 for x less than 2, 1 over 8 square root of y over 2 squared, minus 2 the square root of y over 2. And that is, yes, it's x less than 2, but we really want to replace that for y. So that's the square root of y over 2 is less than 2. The square root of y over 2 here is between 2 and 4. And obviously it's going up to 1 for the square root of y over 2 being greater than 4. Obviously we need to get rid of that square root of y. We need to actually have our inequality properly defined with actually without the square root and the 2 in it. So finally, we have gy equal to 0 for y is now square times it by 2 and squaring it. That's going to be less than 16. And 1 over 8 y over 4 minus the square root of y for y between 16 and 64, and 1 for y greater than 64. So that's it. That's the CDF. We don't need to do anything more because it only wanted the CDF in this particular question, so we didn't have to refer to the PDF either at the beginning or the end because it wanted the CDF. And so that's it. But we do need to change the inequalities at the end. And so that's it done. If I had the time, I would check that this starts off at 0 and ends at 1. If you put 16 in, does it start off at 0 and end at 1? It does appear to start off at 0. Put 64 in, we get 64 divided by 4, which is equal to 16. Take away, yeah, it does seem to at least start off at 0 and end at 1, which is a nice little check. Doesn't mean it's right, it just means we haven't actually found an obvious error. Okay, let's do another example. Okay, let's have a look at this example. Oh yeah, more care needs to be taken, much more care, because of the reciprocal, because something strange is going to happen for the inequality. For example, if you have 1 over x being less than or equal to 2, then that actually implies x has got to be greater than or equal to half in order for that to be correct. So because the direction of the inequality changes, it's a little bit more care needs to be taken. Okay, so let's do the question again. Now, and also we're going to have to do quite a bit of work because we need to get the CDF first because it's the CDF we're after before we of the original function before we can do any kind of manipulation at all. So let's do that. Fx is going to be this integrated. So remember that's 3 over 2x to the half. So fx is going to be equal to 3 over 2 x to the 3 over 2 times 2/3 plus c. So that's equal to x to the 3 over 2 plus c. And we can say in this case, because f naught needs to be equal to naught, that's going to give us c equals to naught. So fx, my CDF, not fully defined, but the function bit that is of interest is x to the 3 over 2. Oh no, it does say find it, and because it says find it, I think we better fully define it in this particular case because that's what it's asked for. If it didn't ask for it, then I wouldn't bother, but it has asked for the CDF. So it starts off at 0, and x is for x less than naught, x to the 3 over 2 for x between naught and 1, and 1 for x greater than 1. And so I wouldn't need it, but it has asked for it. It says find it. Oh no, it hasn't. It hasn't. My apologies. I didn't need that because it said find a cumulative distribution for y. So I didn't need to fully define it like I just did. So now we want to find the cumulative distribution for y. We're going to call it capital G y. That's equal to the probability that some random observation of it is less than a particular value y. So then now we know that y is equal to 1 over the square root of x is less than or equal to y. So as I say, we have to be very careful here because 1 over the square root of x, we can square it, all right. 1 over x is less than or equal to y squared. But if we take a reciprocal both sides or whatever, the inequality is going to change direction. So it'll be x is greater than or equal to 1 over y squared. So that's quite important. So that gives us the probability that x is greater than or equal to 1 over y squared. Okay, but remember, now the inequality is going the wrong way round. So we have to reverse the inequality, and because it's 1, that will be 1 minus p x is less than 1 over y squared, or less than or equal to, doesn't really matter. Okay, it's using the fact that the probability of it being has got to be added up to 1. So that's equal to, now we've got back to our PDF of our original CDF of our original function, because remember the CDF here refers to the probability that x is less than or equal to some value x. So that's equal to 1 minus the probability, so 1 minus f of y squared. So we're going to replace y squared in this function, including the inequalities for it. So gy equals 2, and it has asked for it fully specified now. So we're going to go from, well, I don't know, maybe we aren't going to 0 and 1 because of the reciprocal. We'll see. Let's figure out this inequalities first. Let's just work out the function bit first. So that's 1 minus, and we're putting 1 over y squared. Apologies. It's obviously 1 over y squared there. We put in 1 over y squared into our function. So that's into here. So that's 1 over y squared to the power of 3 over 2. Now, here's the thing. Our inequality is for, we're replacing my x with 1 over y squared, being between 1 and 0. Okay, being between 1 and 0. So I think we need to be a little bit careful in the next bit to get our fully specified bit in properly with this. So we've got g of y equals 2. Right, so it's going to be 1 minus, this bit here is going to be 1 over y cubed. Okay, 1 over y cubed. And the y squared, or the y, we're going to take the square root of it. Y has got to be greater than, clearly got to be greater than 1. But that's it, because if you think about it, if y is greater than 1, then the number will be a fraction, basically. Y is greater than 1. So we don't need a 0 otherwise or anything like that in this function. We don't need 0 and 1 and this kind of stuff here, because it's fully got, a bit like the exponential function, we've kind of fully done it here with this, because y can actually take any number. Y can be as large as we want and it will still be greater than 0. Okay, you could put less than infinity here if you wanted to be, what I think is a bad thing to put really, but it's actually, because 1 over 0 is in kind of nominally kind of a bit of dodgy maths, but is equal to infinity. So that's y is greater than 1 is the inequality for that, and we don't really need anything else. Okay, we could say 0 for y less than 1, but what's the point? We've kind of already got it by saying that y has got to be greater than 1. And certainly y isn't limited by any number. It can be as large as we want it to be. So the 0, 1 minus y cubed, and 1 wouldn't be appropriate here. So that's it. Okay. Apologies, just forgot to answer the question, finish the question, which we actually were asked for the PDF, which means differentiating. And then there's a short part about the expectation of y squared, which I might as well do as well. So to find the PDF, we just need to differentiate, which is easy enough. So gy, little gy is equal to big gy differentiated. So differentiating that, we're timesing by -3 and taking 1 from the power. So that is equal to that. And it's specified for the values y greater than 1. And we could put 0 otherwise, just in case they're going to be... don't think he'll worry too much because of the fact that it's kind of... it's an asymptote on the function, but I'll put the 0 otherwise anyway. And then the next bit is e to the y squared, a little extra part, kind of almost like a bonus thing. Yeah. So e to the y squared will be equal to the integral. Now, of course, this is taking any values from from infinity to 1 of y squared times 3 over y to the 4 dy. So that's the integral of 3y to the -2 from infinity to 1 dy. I'm not going to do the work with the limits that you should do in pure maths here, because I want to get on to the next bit, and I'm sure in the stats paper they're not going to worry about it. It's only asked for find it, doesn't. So we add 1 to the power, so that's 3 to the, and divide by that number, so it's -3 over y between infinity and 1. So that's going to be equal to 0 take away -3 over 1, which is equal to 3. Okay, so here's something slightly different. In this question, it's not about a function, it's about different observations of the same random variable and taking the largest one. And there's a particular way of dealing with this. I haven't seen this many in past paper questions, but I've certainly seen it in textbooks, so I think we better have a look at it. So we've got f. This is a continuous. The original is continuous uniform, which we're sort of be familiar with. This, because it starts off at 0 and ends at 10, was going to have a CDF 1 over 10x, with x varying between 0 and 10. Again, I'm not bothering to fully specify it. We want the random variable for g, say, of y, which is the probability that y is less than y. Now, here's the conceptual thing we need here. It's basically what we need here. We want the largest one of them to be less than some value. So in order because we're taking the largest one of them, and we're taking 3 observations, that's equivalent of saying all 3 values of x have got to be less than this value. All 3 observations of the random variable x have to be less than this number y, which happens to be the largest one of them. So that's probability of x less than x cubed, basically. So x less than y cubed. So that gives us 1 over 10 y cubed. So that's y cubed over 1,000. That's the CDF of it. But we want the PDF. So the PDF is going to be equal to little g of y, which is this differentiated, which will be equal to 3 over 1,000 y squared. And let's fully specify it now. So that's between y 0 and 10 and 0 otherwise. So we're looking for values which is the largest of this three. It's worth looking at the PDF of this. The PDF of the original one, PDF, not CDF, is just a flat line between 0 and 10. Whereas the PDF of this is a quadratic and it's got the mode kind of at the end. Well, that's not surprising because we're finding the larger of the observations of this one. Okay, as I say, I haven't seen it on any past paper questions, but we never know. That's how to deal with those type of questions. If you're looking for the larger of them, you just deal with it in that way. Okay, that's it. Hopefully we've had a reasonable kind of set of view of this topic now. Okay, that's it. Bye.